All right, I want to talk about the capillaries here. So what we have going on, there we go. What we have going on is this is our arterial side, and then this is our venous side. So this is blood coming from the heart that's oxygenated, and this blood going away from the heart being deoxygenated. So there is some sort of exchange that occurs here in order for the blood to become unoxygenated and that oxygen to get to like the tissues and stuff. And so from our capillaries and the bloodstream, and then come back in via unoxygenated and carrying some other crap as well. So the first thing that's going to happen here is our blood's coming in, and it's coming in pressurized. Now we do have this pyloric sphincter here, which is able to pretty well regulate the pressure that we experience inside this cavity. But for the most part, this is going to be considered, this right here is going to be called our hydrostatic pressure. And that has a value of about 30. And actually, I'm going to write it here, but I'll draw it up here, better. This is going to be called our ICF, which is actually a value of about 3. Point being is that there's pressures being pushed out into the environment, the HP being caused by the blood pressure, and the ICF really being caused by these little guys up here, which are our lymph nodes, or not lymph nodes, lymph ducts, and they're causing a negative pressure sucking up, but we're just going to consider the value 3. And then we also have albumin, which is just a blood protein, but it's non-permeable, so it can't cross the membrane. So what is good, that means it causes an osmotic gradient. So the gradient coming in, we actually call that BCOP, and that has a value of about 28. And then we have proteins that I forgot to write on this side. We have proteins like, they could be anything, could be albumin itself, but unlikely. Just another type of protein that is negatively charged that attracts water to it. And this value is going to be called our ICOP, which has a value of about 8. And just for math's sake here in a second, I'm actually going to write this value as negative 28 because it's opposing our pressures. It's not actually negative 28, but that'll make more sense in here when we do some net factors, which we're about to do now. So net factors, this is going to be our net hydrostatic pressure over here. Now going out, we see 33 is what we're experiencing. And then over here, we're experiencing 28 minus, we have 28 coming in and we have 8 going out. If going outs are positive, we're going to think of this as negative 28 plus 8, we're going to experience a negative 20. But if I combine these two to get my net, or my total that's my net osmotic. So if I want to get my total capillary pressure that's going on here, I'm going to see 33 minus 20 is equal to 13. So I have a net 13 moving outward, hence why my green arrow has an arrow, or my green line has an arrow. Again, that's not really negative 28, and but for the math's sake, I like to just show that, hey, these two cancel out because of the different vectors and the direction that they're pointing. We divide this line here because these are separate. Now, that's to get the blood, or to get the blood cells and the oxygen and everything else out of our system. But in order to get them in, we have to be able to pull something back in, or else we're going to get edema, which we'll talk about here in a second. So on this side, because remember, this was induced by blood pressure, but now we don't have that. So this, our hydrostatic pressure is now only 10. This is still only 3. This is still negative 28. And then this is still 8. Remember, HP, ICF, BCOP, ICOP. ICOP going out, BCOP coming in. So again, my net hydrostatic pressure is only 13. This is still going to be negative 20. When I combine the two, I'm going to see something pretty drastic like negative 7 between the two, which means we're going to have a net force coming in. And so my green arrow is pointing in. Now to talk a little bit more about what's actually driving these things, just to further illustrate, I have hydrostatic pressure that's being caused by blood pressure. My ICF is really being pulled by the lymph dudes over here. And it's confusing, but we actually normally call this value -3. We call this value +30, but we ignore the negative. It's confusing that way. This albumin is what causes our BCOP. And then we have our blood proteins. I'm just going to write like these that are negatively charged. And that's actually what causes our ICOP. So it's interesting, from side to side, our BCOP and ICOP aren't going to change because we have the same concentration of albumin and blood proteins. And even from side to side, our ICF isn't going to change because the lymph nodes from side to side are still lymph ducts are pulling the exact same amount of pressure. The only thing that changes is the pressure that's coming in from the body via the blood pressure. Most of it's kind of leached off into here. We still have some pressure, but our concentration gradient is ultimately pushing this way, which causes fluid to come back in because of the osmotic pressure. So here it's hydrostatic pressure that pushes it out, and here it's osmotic pressure that pulls it back in. I want to talk about edema. So edema is what happens when all of these really nice numbers that we got, something gets messed up. Let's use histidine, for example. So histidine is something that comes in and it makes these capillaries way more permeable by literally poking holes in them. It takes them from a continuous capillary to something more like a sinusoidal capillary. So we're going to put holes in these. Now these holes are going to allow things like albumin to come out. When albumin comes out, those unchangeable BCOP, ICOP numbers, well, now they're changing. And this -28 might go to, I don't know, -10 or something like that. But where is it going? Well, that number is being transferred over to the ICOP. So now we have an osmolarity gradient that's pushing from -10, we lost 10 here, gain 10 there. Now it's 18 BCOP, that's ICOP. No, it's not necessarily 1-to-1, but the idea being is that if we have holes that brings proteins out, and now our concentration gradients are so messed up that water, instead of coming out, or when it goes out, it might not want to come back in. So it's just gonna stay out, it's just gonna hang out there. That results in swelling and swelling and swelling, which we call edema. Alright, here we have the heart, and we have your aorta coming out of the heart, and on this little super exaggerated bulb thing, we have something called the baroreceptor. So the baroreceptor is just a regulatory mechanism in which our body can monitor our blood pressure, and that's actually going to feed back to the brain, and the brain's going to control a bunch of stuff to make sure we don't die and we're getting appropriate blood flow to everywhere. So if I were to draw this mechanism out, first thing would happen is we're at the baroreceptor, right? Baro. Now the baroreceptor is going to measure blood pressure, and it's going to send that information to the brainstem, straight above the pons. Now the brainstem has a few options as to what it can do. If it needs to upregulate blood pressure, first thing it can do is it can send a signal to alpha-1 receptors on blood vessels. It can either do dilation or constriction, and we'll come back to that here in a second. The main function it's going to take is it's going to actually go to the adrenal medulla, and it's going to cause a release of epinephrine and norepinephrine, which is going to then go and bind to beta-1 cells on heart and do the whole increase ionotropy. It's going to increase ionotropy and increase chromatropy. And it's also going to it's also going to go to beta-2 receptors on cardiomyocytes. Beta-2 on cardiomyocytes, which is going to cause dilation. The other pathway it can take, sorry, I've been covering that the whole time, my bad. The other pathway it can take is our baroreceptor can go to the brainstem, and it's actually going to activate the parasympathetic route, and it's going to attack the M2 receptors on the heart, and then that is going to ultimately cause a decrease in, that's going to cause a decrease in chronotropy, also ionotropy, making higher lusitropy, and it's all related. Decrease, and we're just going to write decrease heart rate, because that's essentially what the point is, right? And then that's again going to all feed back to there, and same thing with these guys. These can also feed back to the baroreceptor, because they're all affecting heart rate, aka blood pressure. It's all interrelated, right? So that's how the whole process works, and the more the baroreceptor stretches, the more we go along this blue route. Oh, something I forgot to mention is the part of the, it's not the parasympathetic system, but it's a parasympathetic-like response, is since alpha-1 receptors aren't innervated by the parasympathetic system, alpha-1 we can do constriction or dilation, which is that, or constriction, which is our sympathetic. Okay, so as our blood pressure increases, our heart or our baroreceptors are going to stretch even more, which is going to feed through any of the blues or the red systems, because that's saying, hey, too much blood pressure, we need to calm this down. So baroreceptor would stretch more, and it's going to activate our parasympathetic routes, decrease inotropy and increase lucidotropy, which is going to feed back to the baroreceptor, and it's going to be this constant kind of push and pull deal with the M2 receptors and everything. If we were to have a sudden systemic drop in blood pressure, what we would see is that our brainstem is going to flood our sympathetic route and use that to increase blood pressure again. So let's say I'm sitting down, for example, and as I go to stand up, I'm going to have a sudden drop in blood pressure due to the increased venous return, and then that's going to activate the adrenal medulla. The epinephrine and norepinephrine are going to be dumped. Those are going to activate with beta 1 and beta 2 receptors. Beta 1 is going to cause that whole cascade for increasing inotropy through increasing CMP, the PKA, that whole deal. And beta 2 is going to cause cardiomyocytes to dilate, that's not cardiomyocytes, cardiovasculature. Cardiovasculature, like our aorta, to dilate. Now, even though that's a little counterintuitive, why is it dilating to increase blood pressure? That's just to get more blood flowing, since it does have other effects besides just trying to increase blood pressure, like increase blood flow to all the important places like the heart and the brain. And then again, that's going to feed back. Now, we do have a parasympathetic undertone always, and it's just this degree of activation by the parasympathetic system that's saying, hey, slow the heart down, that way we don't just get super out of control and send a cascade. All right, I want to talk about these three topics here in relation to blood pressure. First things first, the myogenic autoregulation system. So what this is let's say we have a huge increase in blood pressure, or any increase for blood pressure for that matter. And what's going to happen is it's actually going to increase, or it's going to cause our blood vessels to want to widen, because we're trying to force more muscle through it, assuming our blood vessels have elasticity. Now, but as they widen, just like what we see in the heart, is that's actually going to cause more voltage or more mechanically gated calcium channels to open, and then that's going to then induce more smooth muscle contraction, which will then cause our blood vessel to dilate. So we can say this helps fight against increase in blood pressure, or increase in blood pressure. Well, I guess that's not true, because actually as it dilates, or as it gets bigger, then it's going to get smaller. So this helps increase blood pressure. So just explaining that back one more time, as we push more blood through it, our blood vessel naturally wants to dilate, but since the goal, in this case, if we're increasing blood flow, is probably to increase blood pressure, then we're actually going to get a dilation, or as the arterial increases in size, that brings in the calcium, and then it's going to constrict and make sure it stays nice and tight. We also have paracrine signaling.
So paracrine signaling happens when we have a decrease in blood pressure, specifically in a located or in a specific spot. And paracrines are just like nitric oxide, not nitric oxide or any other potent vasodilator. But the idea of this is to increase blood flow. So let's say we had an occlusion somewhere in our body. Let's say an occlusion in my arm. Everything down here is not going to be getting enough blood. So what might happen is I might have some paracrines that are going to be signaled right where that occlusion is to cause extreme vasodilation. That will then open up blood flow and get, hopefully, if I'm not dying, be able to continue my blood flow through my arm. So it helps blood flow. And it also will naturally, the part with this thing you talk about called reactive hyperemia. So reactive hyperemia is what happens when I have those paracrines and they cause that potent dilation. I'm able to restore that blood flow, and that part's going to be called hyperactive or reactive hyperemia, because I have a hyper amount of blood flowing through my arm than I normally would once that occlusion's fixed. Sympathetic regulation is just our typical of signaling of epinephrine and norepinephrine to the alpha-1 receptors. But this can actually help with vasodilation and vasoconstriction. So if we have a lot of epinephrine, let's say high, let's just call them, well, we'll call them epinephrine, sure. If we have high epinephrine, this could be any catecholamine really, but if you have high epinephrine, that's going to increase blood pressure, and then if we have low epinephrine, that's going to decrease blood pressure. And in this case, this would be constriction, and this would be dilation. This one especially works in conjunction with the baroreceptor, because the baroreceptor is constantly sensing pressure going to your brain, or your brain stem, and then your brain stem signaling to everything else like, hey, we need to put more epinephrine, or we put less epinephrine, and it's just, it's a good cycle.